Okay, hello everybody, and welcome from Berlin. I'm happy to introduce today's speaker in our ENLA series, Volker Mehrmann. Of course, Volker is so well known that he hardly needs an introduction to our community, but let me still say a few words. Volker has made numerous important contributions in various fields ranging from core linear algebra and matrix theory to modeling, simulation, and optimization of multiphysics systems. He has been awarded many prizes. He got an ERC grant for his work on this multiphysics system problem. And he's a SIAM fellow and many other things. Equally impressive, I think, is his record of service for our academic community. Just two examples: he was the president of GAM, and he currently is the president of the European Mathematical Society. In the last few years, Volker has been interested in the theory and numerics of Port-Hamiltonian systems, and that's also the topic of his talk today. All participants on Zoom or YouTube are welcome to write questions. So you can either use the Zoom Q&A or the YouTube chat to write your questions. The questions today will be monitored by Daniel Kressner on Zoom and by Bart van der Eycken on YouTube, and they will be asked at appropriate times, either during the talk or after the talk. So please, Volker, go ahead with your talk about robustness of linear algebra properties for Port-Hamiltonian systems.
Yeah, thanks to the organizers. Thanks very much for organizing this electronic seminar. It's a great pleasure to speak here and to talk about my favorite topic. And as you may have noticed in the title, I have written the linear in the capital letters and the algebra in small letters. And this is on purpose because in this talk, I will mainly talk about the linear algebra problems. Okay, let's start. Let's start with my plan for today is multifold. I will have interruptions where you can ask questions. I have also a part which I may not get to depending on the number of questions on passivity, but let's see how far we can get. So many of you have seen one of my favorite examples, industrial examples that I'm working on. This, what you see here, is a car disc brake. You have the disc, you have the brake pad, and sometimes these make funny noises, and this is a frequent and very annoying phenomenon, not only with cars, but also with trains and bikes. It's important for customer satisfaction, but it's not necessarily a safety risk. It's a non-linear effect that is very hard to detect and to estimate that when it will happen. And the car industry is trying for decades to improve this by changing the design of the brakes and the disc. And the question is, can mass help? And for many years now, I'm running a project with two colleagues from mechanics, Norbert Hoffmann from Hamburg and Utz von Wagner from TU Berlin. And it's supported first with an industrial project and now with a research project by the German Science Foundation within the priority program called nicely Calm, Smooth, and Smart. And the goals are to develop brake models with all the effects that may occur and that may cause squeal, to simulate the brake behavior for many different parameters, disk speed, material, and geometry parameters, and in particular to analyze the stability of the system. And at the moment, we are working on the design optimization, including in particular to remove the squeal by so-called shims. A shim is what you see here in the bottom, is a little device which you glue to the brake pad. And if you want to learn more about this, there's a joint paper with colleagues from my group and from the mechanics group. Okay, what is the problem behind it? When you write a mathematical model, it's an eigenvalue problem or a differential algebraic system. It's a finite element model. mass matrix times second derivative plus C of omega times Q dot plus K of omega Q, where M is a symmetric positive semi-definite, in particular singular matrix. C is containing 3 parts. It's symmetric matrix for the classical material damping, a skew symmetric matrix which models CG, which models gyroscopic effects, and symmetric matrix CR, which models friction-induced damping. And I should note here that this is generated from data, so that's a fitting problem that leads to this problem. And then there are 3 matrices that contribute to the K. There is a symmetric stiffness, the classical stiffness matrix, a matrix which models the circulatory effect, and a geometric stiffness matrix. And many of these coefficients here depend on parameters. I display here only the rotational speed of the disk when it rotates. That's omega, and it's divided by a reference frequency. Okay, so that's a second order differential equation. And what do we usually do? To do eigenvalue analysis, we make a Fourier ansatz. We say that Q of t is e to the lambda t times v. All this depends on the parameters, and we get a polynomial eigenvalue problem. And for many years, I've been working on linearizations of this. Let's look at the simplest linearization we know. It's a companion form. So we have lambda times this matrix here, C minus C minus mi, and Ki, and combined vector of the velocity vector and lambda, the eigenvector and lambda times the eigenvector. So we have such an eigenvalue problem, and the analysis tells you that the likelihood of a break to make these funny noises is correlated with the magnitude of a positive real part eigenvalue of this eigenvalue problem. And if we don't have any breaking, then the system is stable. So all the eigenvalues are in the left half plane, and passive. That means no energy is generated from the system. Energy is only dissipated. And in order to find out whether this squeal happens, we need to find out when an eigenvalue crosses the imaginary axis. And so one wants to determine the distance to instability and also non-passivity. So how far do we have to tweak the system using our parameters so that an eigenvalue crosses into the right half plane? And then if this is, then if we know, then we can modify the system, in particular modify the damping, which is in this matrix C here, for example, by changing the design, by adding these shims, or by putting in a feedback control. So let's go back to our second year course on differential equations. What is the classical definition of stability for ordinary differential equation? Solution x of an ODE, x dot equals f of x and t, with initial value x0 is called stable if for every epsilon greater 0 there exists a delta, such that the initial value problem with the perturbed initial value is solvable on the interval that we're looking at for all x0, perturbed x0 in a small ball around our correct initial value of size delta, and the solution stays within an epsilon ball of the true solution. And it's asymptotically stable if it's stable, and at the same time, the solution goes, the difference goes to 0. So, and by shifting the argument, we can always assume that the true solution is a 0 solution. So that's a classical definition. If we are in the linear algebra setting, so if we linearize around a stationary solution, then we get a linear ODE, x dot equals ax. And then we can characterize stability via the Jordan canonical form. So the well-known theorem, I don't know who did it first, probably Lyapunov, consider a constant coefficient system with a real n by n matrix, it's asymptotically stable if all eigenvalues of A have negative real part, and it's stable if all eigenvalues of A have non-positive real part, and all eigenvalues with real part 0 are semi-simple. That means they have no Jordan blocks of size bigger than 1. So that's very nice. It's a classical result. We can compute the Jordan canonical form and check stability. However, we all know in our community that the Jordan structure is hard to compute numerically, and typically one rather uses pseudospectra, and we will have Nick Trefessen speak a few weeks later here, and the famous book by Trefessen and Embry tells you all about it. But one could ask the question, how far is a system from a stable system? If it's not stable, or the other way around, if you have a stable system, how far are you away from the unstable system? And that will be one part of my talk. Now, these differential algebraic equations, like the model of the break that we had there, have the same definition of asymptotic stability. So the problem is only that you cannot use arbitrary initial values, but they have to be consistent with the algebraic equations are in a system. And there's also a problem with the regularity of the right-hand side that one has to look at. So if one linearizes around a stationary solution, then one gets a linear DAE, EX dot equals AX plus F. And you can analyze that in a similar way with the help of the Kronecker canonical form. And since I don't expect everybody to know about the Kronecker form, I will give it to you in a second. In DAE, in differential algebraic equations, one has to be careful because of the initial conditions and the regularity. And this is in particular true if one has that the problem is perturbed in the, not only in the initial value, but also in the coefficients of the system. And so then the structure may change completely. So let me recall the Kronecker canonical form. If you have two matrices E and A, and I write this over the complex matrices, but there's a real version as well, then there exists some singular matrices S, n by n, and T, m by m, such that for all mu complex numbers, S times mu E minus T times T is equal, there's an equal sign missing here, to a block diagonal matrix where the blocked entries have the following properties. So the J blocks, these guys here, they are standard Jordan blocks. That's the ones that we know from the Jordan canonical form. Now it gets a little bit smaller. The N blocks, they look also like Jordan blocks, but except that the Jordan blocks are at the lambda term. They are corresponding to the eigenvalue infinity. So 1 over infinity is 0. So they are the eigenvalue 0 from the reversed pencil. And then there are these rectangular blocks with one more column than rows or one more rows than columns. And if these occur, then the problem is a singular pencil. So the biggest size of such an N block is called the index, and the sizes of the rectangular blocks are called the left and right minimal indices. And the system is regular, the determinant, so if it's square, and the determinant of mu E minus A is not identically 0. So it's much more complicated than the Jordan canonical form, but it has a similar form. So if you do linear stability analysis of differential algebraic equations, then you can consider linearization around stationary solutions. Then we get a system EX dot equals AX. And let's look at the square case here. And because if it's non-square, we automatically have a problem that the system is not solvable or not uniquely solvable. It's asymptotically stable if the pair is regular, so this determinant doesn't vanish identically, if all finite eigenvalues have negative real part and all infinite eigenvalues are semi-simple, the problem has index 1. So similarly for stability, it's stable if it's regular. All eigenvalues have non-positive real part and all real part eigenvalues, and I put infinity here on the imaginary axis, are semi-simple. So in contrast to the ODE case, we have not only to check the eigenvalues, if there are any, but we also have to check the infinite eigenvalues, and we have to check regularity. And as the Jordan form, the Kronecker structure is very hard to compute numerically, almost impossible under perturbations. Again, one may use pseudospectra, and there's a very nice paper on this by Embry and Keeler for the analysis. And then one can ask the question, how far are you from an unstable system? How far are you from a singular system? And how far are you from a high index system? So can small perturbations bring you to a bad problem? And the second question that one should ask is there any hope to check something like this for a real world problem like the break? So are there any questions so far? Please use the chat or questions and answers.
Volker, as far as I can see, there are no questions in the Zoom.
Okay.
And on YouTube as well.
Then I will continue.
Yeah.
So in order to answer this question, whether there's any hope, we will look at a new way of modeling. So, and the way to do this is to use structure. And those who know me for many years know that structure is one of my favorite things. So we will do a new modeling approach. So what are the goals? We want to find a representation that's good for model coupling, because these finite element models are pasted together from pieces. We want that it's good for discretization, finite element, that it's good for model reduction, to make fast methods, for stability analysis, and that it should be close to the physical system that it comes from. And is there such a jack of all trades? And the idea that came up around 2000 and is very popular nowadays is to use energy as a common quantity for every different physical system, and to use so-called Port-Hamiltonian systems to do the modeling. So let's look what such a Port-Hamiltonian system look like. And I will give you the general definition in the nonlinear case, and I will come back to the linear case in a second. So we have an ordinary differential equation, x dot equals j minus r times the gradient of a function h. Then we have b minus p times an input u. And then we have an output y, which is b plus p transpose times the gradient of this function h plus a feed-through term s plus n, symmetric plus q symmetric part. H is the Hamiltonian, and that describes an energy function. A typical function would be kinetic plus potential energy. J, this matrix is a coefficient function which describes the energy flux among energy storage elements in the system. So that's skew symmetric. R is a positive semi-definite matrix over here, and that describes energy dissipation or loss in the system. If R is equal to 0, we would have conservation of energy. B plus and minus P are the ports. So that's the input port, and that's the output port here. And S plus N is just a feed through. In many cases, this term is not there. And in the infinite dimensional case, these coefficient functions are operators that map into appropriate function spaces, but we will look here at the finite dimensional case. So why is this a good idea to use this? First of all, these Port-Hamiltonian systems generalize classical Hamiltonian systems. That's a big class of physical systems in mechanics. The conservation of energy, which you have in classical Hamiltonian systems, is replaced by a dissipation inequality. That means that the Hamiltonian, this energy function, at time t1 minus the Hamiltonian at time t0 is bounded from above by the integral from t0 to t1 of the inner product between input and output, and they have the same dimension. What are the other nice properties? The really important fact why they are so important is that you can take such Port-Hamiltonian systems and you can interconnect them in a power conserving way. So for example, put the output of one system into the input of another system, or do a linear combinations. And that means models can be built in a network-based, modularized way. So you can build your system from pieces. And the Port-Hamiltonian structure allows to preserve physical properties under Galerkin projections, so finite elements, for example, and model reduction. And the physical properties of the system are encoded in the algebraic structure of the coefficients, is symmetric and semi-definiteness, and in the geometric structure associated with the flow of the differential equation. So why are they so important? Because almost all real physical systems are Port-Hamiltonian. So whenever a system dissipates or conserves energy, then it can be formulated as a Port-Hamiltonian system. Examples are energy networks like gas, oil, power, or district heating networks, classical water supply networks, thermodynamics, fluid dynamic like Navier-Stokes equation, mechanical system, quantum mechanical systems, wave phenomena, astrophysical phenomena, and even market models have been put into this structure. The difficulty sometimes is to find the right representation, to find the right variables, because in the physical literature, typically variables are used that are not common, like in our mechanical system of the brake. Typically, people write it in the displacement and the velocities. To make it Port-Hamiltonian, you would use displacements and momentum, but momentum in the linear case is just mass times velocity, so it's very easy to go from one to the other. So they are pretty universal systems, and that's why I like them a lot. And there's another nice property of them, that is they are automatically stable. So if you don't have an input or output in the system, so if this inner product of input and output is equal to 0, then the system is stable. And if the dissipation matrix R is positive definite, then the system is asymptotically stable. So pH structure gives stability and even robust stability under structured perturbations. And the Hamiltonian is, for those who do nonlinear stability theory, is actually a Lyapunov function. And then if one looks carefully at this representation via Port-Hamiltonian system, there's much more. One can see, and this is work I've done with Christian Mehl and Punit Sharma, that the stability radii, the perturbation distance, are much larger for this structured perturbations in this class than if you just do arbitrary perturbations. And in the end of the talk, I will come to this joint paper with Richard Aliyev and Emre Mengi, where we compute stability radii for the large problems like the brake. So the structure automatically gives you nice physical properties. But as I told you, our brake system and many other systems are differential algebraic systems. There is a very general definition of Port-Hamiltonian differential algebraic system. I'm not going to give it to you. I'd rather give you the linear version. There's joint work with Ricardo Morandin from the end of last year. And we showed that we get a formulation which is invariant under state and time diffeomorphism, that we get asymptotic stability even though energy enters via input and output, and the dissipation inequality is strict as in the ODE case. And we get the invariance under connection, under Galeckian projection, and there's even an underlying Lagrangian structure and a symplectic flow for those who know what that means. But let me give you the linear version. So a linear constant coefficient DAE, which has this form, EX dot equals, and now we have a matrix here, J minus R times Q times X, and the rest is exactly the same as in the ODE case. So in the previous ODE case, we had J minus R, and then we had the gradient of the Hamiltonian. This is slightly different here. The Hamiltonian in this case, in the quadratic Hamiltonian case, looks like 1/2 X transpose QT EX. So the Q transpose and the E come into the play here. They can be rectangular matrices. This is the quadratic energy function, and the Q shows up here and the E shows up here. And this is called Port-Hamiltonian DAE if QTE is ETQ. So QTE is a symmetric matrix and it's semi-definite. QTJQ is skew symmetric, and this matrix W, which is formed from QTRQ, QTP, PTQ, and the symmetric part of the feed-through matrix, this is called the dissipation matrix, that is semi-definite. So that looks a little bit complicated, but think for a moment, if E is the identity, then the Hamiltonian, then Q would be symmetric, and the Hamiltonian is just X transpose QX. If the Q is, for example, also invertible, then this is even definite, and this property is immediately satisfied, and then you can take the Q out here, and then you just have R, P, P transpose S has to be semi-definite. And in many applications, Q is even the identity, and the Hessian of the Hamiltonian function is just here, the E. Okay, so now you look at this and you say, hey, rectangular matrix, oh yeah, there's symmetric plus Q symmetric. Can this have any nice structure? And it's surprising. It has surprisingly nice structure. Let us look at the two pencils. The first pencil is just the pencil of E and Q, and the second pencil is the pencil of this system without the input. With skew-symmetric J, semi-definite R, and QTE equals QTE greater or equal to 0. This we don't always need, but in some cases we do. And in a joint paper with Christian Mehl and Michał Wojtulak, we showed the following. First, this pencil is very special. It's two rectangular matrix, but E transpose Q is symmetric. So if this is regular, this pencil, then it's of index at most 1. So Jordan blocks maximally of size 1. So that's this pencil, but that's not the pencil we're interested in. We're interested in the second pencil. And here we get another surprising result is, if you have such a system, now we use semi-definiteness of QTE equals ETQ. And let's for the moment assume that all left minimal indices, so these are the sizes of these rectangular block, one type of rectangular blocks, that these sizes are all 0. Then for this pencil, if we have an eigenvalue of P, then its real part is less than or equal to 0. If we have a non-zero eigenvalue on the imaginary axis, so if mu is I times omega and omega is not 0, then it's semi-simple. So no Jordan blocks of size bigger than 1. you can also characterize when you have eigenvalues on the imaginary axis. Then you look at the deflating subspace corresponding to the part without the R. And then you look at RQV, where V is a matrix spanning the deflating subspace, and this is 0. Kronecker blocks at infinity or 0 can have bigger Jordan blocks, but at most size 2. And if Q is invertible, then also the eigenvalue 0 has Jordan blocks at most of size 2. So you get, for such a complicated structure, you get almost everything we want. So we get asymptotic stability if it's regular, all the finite eigenvalues are in the open left half plane, and the system is index 1. So the eigenvalue infinity is semi-simple. So the only thing we have to check is the positive semi-definiteness of R, or this property here, RQV equal to 0. Then we have all the eigenvalues in the left half plane, except maybe infinity, and that one we have to check. We get stability if P is regular, and 0 and infinity are semi-simple. And we get robust stability also under perturbations, is the distance to instability to the nearest index 2 problem, and the distance to the nearest singular pencil if these distances are large. So the question is, can we compute the stability radii and these distances for large-scale systems? So let me look at the distance to singularity first. So for a general pencil, the characterization and the computation of the distance to singularity is a long-term open problem. It's still completely open, and the difficulty is that you can take such a pencil, as even both matrices are symmetric. The distance to singularity is epsilon, because if you put epsilon to 0, the determinant is identically 0. So the distance to a common null space of E and A is 1. So the smallest perturbation is this epsilon here, and if you have this epsilon here, you can see I put it already, it's in Kronecker canonical form, so you have these minimal indices greater than 1. And there are computational methods to compute bounds by Ralph Byers and Chunyang He and myself, or recently by Nicolas Guillemi and Christian Lubich and myself, and in special cases also with Christian Mehl and Michal Wojtala. But these are bounds. And the question is there anything better with Port-Hamiltonian system? And it's absolutely surprising that if you have a real dissipative Hamiltonian pencil, so coming from a Port-Hamiltonian system, with E and R semi-definite, and here I assume that Q is the identity, otherwise this can be reduced to that case, then the following are equivalent. The pencil is singular, the matrices E and J minus R have a non-trivial, the kernels have a non-trivial intersection, so common null space. The matrix E plus R minus J is singular. The kernels of E plus R and J have a non-trivial intersection, or the kernels of all three matrices E, J, and R have a non-trivial intersection. So in this case, we only have to look at the common null space problem. While in the previous case, the nearest singular pencil was one with a complicated structure in the Kronecker canonical form, and it's so hard to compute these distances because you have to compute the distance to all possible Jordan and Kronecker structures in the system. Here we don't. Here we get it by a common null space, and we can actually characterize the distance to singularity very simply. So take a regular and real pencil, a dissipative Hamiltonian pencil, and take a unit norm vector U, oops, sorry, form this projection U transpose, and then form these matrices delta E, which is PUE minus PUE minus EPU plus PU EPU. and delta R is this matrices with 3 terms, and delta J with these 2 terms, then this pencil here has the property that E plus delta E is semi-definite, R plus delta R is semi-definite, and this is Q, and it's singular. So you can really compute with one vector the distance to singular pencil. So now you optimize over this vector U and define this distance to instability as a sum of the Frobenius norms of the perturbation, where the inf is taken over the set which satisfies the semi-definiteness constraints and the skew symmetric constraint. So define this distance, then the minimal distance to singularity for a real regular system of this form is given by this optimization problem. So you take the minimum over all vectors U, you project the E, this P perp is I minus PU, you project the EU, you look at UT, EU, JU, 2 norm, and this, so this is our function that we can minimize. And the really nice thing is this distance is bounded from below and above, except for a factor 2, by the minimal eigenvalue of this matrix E squared plus R squared plus JTJ. So that means we have a very good starting value for the minimization. So this is very nice. So how about the distance to the next index 2 system? This is also interesting. So take a system which is regular and is index 1. Then the distance to the nearest high index problem is DHI, and the distance to the instability, they are the same. So distance to instability is the same as the distance to the nearest high index problem. And again, it's a minimum over a function that one can optimize, and we get bounds from the eigenvalue of E squared plus R squared between these two distances and the factor of 2. So there's a lot of nice properties that we can have from these problems. So we can compute these distances also in the DAE case if one can minimize this function. So intermediate conclusion, these Port-Hamiltonian DAEs, they are a fantastic structure. One can do the stability analysis, that's very easy. Essentially, one has to check positive semi-definiteness of matrices. We know how to do this with Cholesky. And one has to check the eigenvalues 0 and infinity. And the distance to singularity and to instability in high index are common-null space problems. And so if we model directly with this structure, it makes the representation very robust. And the perturbation theory is much nicer. And this also extends to general nonlinear and pHDAEs and partial differential algebraic equations. And before I ask the question, does it help us for our break? I will make a little break here for questions. Are there any questions?
Yeah, Volker, there are 2 in the Q&A. So yeah. One is by Fräulein Dopico. So you have these DH pencils, and his question is whether this DH pencils, the structure of the DH pencils, induces certain properties of the minimal indices of the pencil.
Yes, it does. Actually, the minimal indices in this form, as I showed you, the common-null space property that I showed you is exactly saying that the minimal indices can only be of size 1. They are, it's a common-null space problem. So there are no higher order minimal singular blocks.
Okay, that's pretty clear. The other question which came up is if you have, by Nguyen Tan Son, if you have such a Port-Hamiltonian system, so how important is it to preserve or exploit this structure when simulating or performing model reduction?
This is extremely important because it's well known, if you take a classical physical system like such a mechanical system and you do model reduction and you don't do it in a structure preserving way, then you may get instability due to the projection, due to the finite element discretization. And that's a very, very important problem in the electronics industry. I probably will not have time to go into this, but a big problem there is to find the nearest perturbation to bring you back to such a system. And if you use the structure, you get it for free.
Okay, thanks, Volker. These were all questions for the moment.
Yeah. Okay, let's apply this to our break squeal. So I drop the dependence on omega now for the moment, and I write it in this form: m plus d plus g times q symmetric plus q symmetric, and k plus n, k semi-definite and n arbitrary. So this is a structure that we had. M noted, recall that M was singular but diagonal, and so the infinite structure can be detected easily. There's more difficulties if one uses other finite element ansatz functions, but I will not talk about this here. The system is robustly regular, that one can show, so the distance to the nearest singular pencil is large, and the question, does our analysis help there? So first of all, we have squeals, so the system cannot be stable. So this is not a Port-Hamiltonian DAE. Where is the problem? So let's try to write it in a Port-Hamiltonian structure. So write it in first order, but I do it different as in the classical companion form. I take this matrix J, this matrix E of M and K, and Q is the identity, and R is D, the damping matrix, which was semi-definite, plus, and here is the troublemaker. It's a symmetric, indefinite matrix which perturbs the damping matrix. So what do we lose? We lose the semi-definiteness of the R matrix. So R consists of two parts, a semi-definite part and an indefinite part. So this instability and the squeal arises only from this block. And where does it come from? So we again have a dissipation inequality for H. H is Z transpose EZ, and if this is a common vector. And we have H of T2 minus T1 is bounded by the integral. But now here we have something which is bigger than 0. And so there's room between H, the difference in the H's and this integral. And in this room, in between here, there is where the instability comes from. And where does this come from? If you break, which is the purpose of a break, you add energy to the system, and that makes the system unstable. The nice thing is the perturbation N is restricted to the break pad, to the finite element nodes on the break pad. So this is typically a low rank matrix compared to the whole system size. So for example, when this is 1,000,000, this is about 2,000. So one can also see this in a different way if one looks at the Port-Hamiltonian behavior formulation of this Port-Hamiltonian DAEs. So one puts all the variables, the state, the input and the output in one vector, and adds the feedback, output feedback, U equals Fy, introduces block matrices, curly E, which is E0, 0, curly J, which is this skew-symmetric matrix, and curly R, which is from the old matrix. That's the old matrix W. And here we have what comes from the feedback, and the Hamiltonian stays the same, except in the new variables. And then this is again a Port-Hamiltonian DAE if and only if the feedback is negative semi-definite. But if you add energy to the system, it's not a Port-Hamiltonian DAE. So this is the problem. So the practical approach for our system is we compute the distance to instability, and then we use parameter optimization to find the crossing point on the imaginary axis, and that is used to optimize the shim. But the problem is large scale, and in order to deal with that, you have to apply model reduction. Let's look for this. How bad is the problem? This is a real break with 850,000 industrial data. And I did the following. I put a homotopy parameter here and brought this damping, this destroying term here in with alpha between 0 and 1. And for alpha equals 0, it's stable. And for alpha equals 0.1, we already have a positive real part. So it's very close to an unstable problem. That was done in a master's thesis by Andre Bekesh. So in order to compute the stability radius, and I will be at the end in a second, we need to compute the stability radii. It's typically not feasible for large-scale systems because now we don't have a DH model because this perturbation makes the R matrix indefinite. But we can compute a reduced model using a Galerkin projection. Then we compute the stability radius of the reduced model. And then we use interpolation at this point to increase the dimension. And that we iterate until convergence. And we do this by preserving the Port-Hamiltonian or the dissipative Hamiltonian structure. And in the DAE case, we also have to preserve the algebraic constraints. And we do a greedy algorithm, which was first designed in a paper by Ali Benamengi, Schwerdner, and Vogt. And we adapted this. And let me not talk about the model reduction, but let me show you the result for the disk break. So here is the rotation frequency omega. We look at the stability radius and we computed it, and you see here around 1050 we have the smallest distance to instability. It's 0.007, and it happens at an omega value of 10 to the 5. We get this stability radius with 2 iterations of our procedure. It takes about 180 seconds, and the resulting dimension from 9,900 goes down to 72 to compute this value. Okay, let me go to the end. I had a chapter on passivity, but I will not come to this. And so this energy-based modeling via Port-Hamiltonian DAEs is very nice for multiphysics and multi-scale problems, not only in the linear case, but also in the nonlinear case. It has a very rich linear algebra structure. You get stability and passivity. You get optimal representations in the ODE case. That's what I skipped. And you have efficient methods for very large scale problems, including model reduction techniques for this case. But there are a lot of open questions. So the Port-Hamiltonian case is not completely settled. There are quite a lot of open problems there. We don't know what the optimal representation is, in particular to deal with the algebraic equations. And we also need efficient methods for the large-scale case. And we need optimization methods to compute these distances that I showed you. And unfortunately, our break-screw problem, like many other problems, is generated from data. So the model is really learned from a learning or approximation process. And so our system has perturbations in there. And the question is, do these perturbations behave differently than the perturbations that we have already looked at? So with this, I would like to thank you for your attention, my sponsors for their support. So part of this was done in the priority program Calm, Smooth, and Smart, but also within other research problems. And it was also funded via the Ministry of Economics within an industry funding project. And now I can come to, are there any questions? Thank you.
Okay, thanks, Volker. We don't have many questions so far, so I will ask you one so that we have a bit more time for others to ask questions. So I would like to ask a question more to the beginning of the talk about this whole theme of robustness concepts in control, which you are following a rather traditional approach, and one could argue that this is possibly too conservative. Whereas in uncertainty quantification for pHDAEs, we do it differently, right? So we try to get some quantity, impose a distribution, let's say, on the perturbations or on the quantities, and then we try to compute statistics of these quantities. So I was wondering, what's your take on this?
So both, my last point that I was making is exactly into this direction. So really when you model this in the modeling, and also there is randomness in the, or in the coefficient. We don't really know yet in a proper way how to put that into the structure, and that's currently under investigation. Indeed, what we've done here so far is a very conservative approach, and it's conservative in the sense that we get a robustness measure in every case. But if you really want to do a statistical approach, you may allow yourself a small probability that you are outside. The question is, can this small probability happen? And I'm not an expert on this, so I really don't have a good feeling.
Okay, thank you. There was a question on YouTube, on the YouTube channel, so maybe Bart can ask that question.
Yes, so the question on YouTube was to say something about the numerical integrators, or the choice that you have to make to integrate these DAEs. And I think that's also related to a question on the Q&A on Zoom.
Yeah, so let me just take such a system back up here. So let's suppose we have given an input u, then we have a right-hand side, and now we want to integrate such a system. At first sight, again, it looks pretty much like a general DAE system. But one can show, that's work of Ricardo Morandin, that if you use the special class of so-called collocation methods with Legendre collocation points, then this structure is preserved, even in the nonlinear case. So these are the ideal structure if you have a quadratic Hamiltonian, and if we have a non-quadratic Hamiltonian, then you can show that the structure is preserved also in the nonlinear case, even if you have a non-quadratic Hamiltonian, but then only up to the order of the discretization method. So there are good methods to do this. We don't have a complete picture what are all the methods that preserves it. If you want to use the most simple method, use the implicit midpoint rule. That is something like when one usually is using the Euler method. Here, the implicit midpoint rule is a good player.
Okay, thanks for the answer. There's one more on YouTube, which is about the application of your brake squeal. So somebody asked, how effective is a passive method like this compared to feedback control?
Yeah, so that's an interesting question. From a control theoretic point of view, I would put a little device on each brake and then measure when the squeal happens, and then do a feedback controller. Actually, you just have to ping the brake with a little ping, then it goes away. Some of you may have seen the movie that I showed from time to time. But this is not effective, and the car industry doesn't want to do it. And so actually at the moment we are looking at other designs of the brake, and my colleagues from mechanics have a very nice idea, which I cannot tell you, how this can be improved. And these shims are what you find in every car nowadays. Every expensive car at least has these shims on the brake. So this is a question of really practical design of such brakes and how they operate, because the brake is a dirty part.
Okay, from the chat, Cliff Moller is asking, are you using supercomputers or laptops?
Both.
Both.
We do model reduction for these big brake models, in particular when we have to run a lot of parameter values. And I only showed you the frequency, the rotation frequency, but there's also material parameters and geometry design, and that is done on a cluster. But once you have a reduced model, almost all of this can be done on a laptop.
Okay, I think we have covered most questions, so I will give the word to Jörg.
Okay, I think I'm back. Yeah, thank you very much, Volker, for this very interesting talk about your favorite problem. Let me pull up the slide. Yeah, I hope you can see it. Yeah, thanks again. Thanks to all the participants this week. Thanks for asking all the questions. And here is the program of the ENLA seminar series for the next week. So next week will be Ilse Ibsen, and then Cliff Moller and Nick Trefethen, and we have more speakers lined up. So tune in next week, same channel, same time, and see you then. Bye-bye.
Bye, thanks.